we will discuss about PFA antenna. What is PFA? PFA stands for planar inverted F antenna, which looks like an inverted F in shape. In PFA consists of a flat radiating patch parallel to the ground plane. One edge of the patch is shorted to ground via shorting pin or plate, which are other types of the PFA antenna. Now we will discuss about them. What are advantages of PFA? It has very low profile, slim of device form factors, ideal for smartphones and small wearable items, easy impedance by adjusting the feed point placement and simple design. Cost effective, it is the manufacturing for this antenna is very costly affordable. Multi-band support, it supports the wideband designs with relative simple modification and enhancing the versatility. Key parameters affecting the PFA performance. Patch dimensions, the length and width of the patch will affect the performance of the PFA. Distance from the patch to the ground plane will also affect the performance of feature by influencing the bandwidth and overall efficiency. Shorting and feed and ground plane size also affects the radiation pattern and overall gain of the antenna. Common applications of PFA antenna are in mobile phones, tablets, IoT devices, embedded systems, emergency technologies, LTE, IoT, Bluetooth, and various other applications of PFA antenna. Now we will discuss about one of the type of the PFA antenna, PFA inverted F, input impedance. The input impedance varies with the frequency and traces a path around the matched point. At the resonant frequency, the impedance is very close to 50 ohms with negligible reactance, indicating good impedance matching at the resonant frequency, making it a maximum power transfer. Away from the resonant frequency, antennas exhibit capacity or inductive behavior, resulting in mismatch and increasing reflections back to the port. And the return loss, we can see that from the graph that the return loss spots show a clear dip at the resonant frequency, indicating good impedance matching at the resonant frequency. Return loss below 10 dB confirms that most of the input power is delivered to the antenna with a minimum reflection backwards. Away from the resonance, return loss increases, signifying mismatch and higher reflected power. Gain. The gain plot shows how efficiently the PFA radiates power in a given direction as frequency rises. Away from the resonance frequency, the gain increases due to impedance mismatch and the increased losses. And directivity. The directivity plot shows how concentrated the radiated power is in a particular direction as frequency varies. Near the resonant frequency, directivity reaches a maximum, indicating stronger and more focused radiation. At frequencies away from the resonance, directivity decreases due to non-optimal current distribution and broader radiation patterns. Radiation efficiency. Radiation efficiency indicates how effectively the antenna converts the accepted into power into the radiated power. It accounts for losses due to conductor resistance, dielectric losses, and surface currents. Near the resonant frequency, the efficiency is high because current distribution and the impedance matching are optimal. Away from resonant frequency, efficiency decreases and losses become dominant and radiation weakness. Total efficiency. Total efficiency is maximum at resonance, where the radiation are optimal and decreases rapidly away from the resonance due to losses. Effective area. Effective area represents the power receiving capability of an antenna. It depends on realized gain on the operating wavelength. Although realized gain increases near resonance, the decreasing wavelength at higher frequency dominates. As a result, effective area shows a smooth decreasing trend with increasing frequency rather than a sharp peak. This is the radiation pattern of a PFA inverted F antenna. It shows the spatial distribution of radiated power from the PFA antenna. The PFA exhibits a broad side radiation pattern with maximum radiation normal to the patch surface. Polarization. PFA typically exhibits a linear polarization determined by current flow on the patch on the shorting element. Proper polarization ensures efficient power transfer between transmitting and receiving antennas. Polarization characteristics remain stable near the resonant frequency, enabling reliable wireless communication at the resonant frequency.
Shorting plate, input impedance. So the impedance locus moves around the Smith chart as frequency varies. The curve passes close to the center, indicating that R is equals to 50 ohms and X is nearly 0. Yeah. So this confirms good impedance matching at resonance, and away from resonance, inductive or capacitive behavior is observed. Shorting plate return loss. So from marker M1, we can see this is the resonant frequency, which is 2.9242 gigahertz, and here the equivalent return loss is minus 12.40 dB. So this shows efficient power transfer at resonance, and reflections increase away from resonance. So as we move away from resonance towards M3 and M4, the reflections also increase. Realized gain. So yeah, I have set the marker M3. So M3 marker is set at 2.92 GHz and the equivalent realized gain is 3.68. 3.68 is nearly equal to 3.7 dB. So this indicates efficient radiation and low gain at lower frequency. So at M1 the realized gain is low because the frequency is 1.2 GHz. Then when we increase the frequency 2.7 GHz, the realized gain becomes 0.55 and again it starts increasing. But after a certain time, see, after M3 frequency it decreases very steeply. So reduced gain away from resonance. So as we move away from resonance, away from resonant frequency, again the realized gain starts decreasing. Directivity. Yeah. So the directivity increases with frequency as the antenna becomes electrically larger and the radiation beam narrows. So as we increase the frequency, the directivity, the total directivity also increases. Right? So maximum directivity of approximately 5.98 dB is obtained near the resonant frequency. So you see, we have got resonant frequency at M2, which is 3 gigahertz. 3 gigahertz here. We have 5.97 dB. So high directivity near resonance indicates effective focusing of radiated power in the broadside direction. And then we observe a slight reduction and decrease in the directivity as the frequency moves away from the this resonant frequency. As we move away from M2 towards M4, if we go, when we increase the frequency 3 GHz, the directivity is 5.75. Okay, a slight reduction at higher frequencies occurs due to the onset of higher order modes and side lobe formation. So this is the reason why again it starts slightly decreasing. Next is radiation efficiency. So here we have got a smooth graph. So radiation efficiency is low at lower frequencies, as we can see from here, due to weak radiation and higher relative losses. So yeah, the efficiency increases with frequency and reaches a peak of approximately 99.8% near the resonant frequency. So we have got resonant frequency at 3 GHz. This is M3. So this is our resonant frequency, and when we see, so this is 99.85% at resonant frequency. This is the radiation efficiency, right? So the high efficiency at resonance indicates higher effective conversion of accepted power into radiated power, and a slight reduction at higher frequencies is observed due to increased conductor losses and higher order mode effects. So when we move away from the resonance frequency, there is a slight drop in the radiation efficiency. Next we come to total efficiency. So total efficiency, the total efficiency reaches a maximum value of approximately 93.5% at the resonant frequency. So at M1, which is the resonant frequency again, 2.92 gigahertz, so nearly 3. Okay, so here we get a maximum total efficiency. High total efficiency at resonance is due to optimal impedance matching and high radiation efficiency. And as we move away from resonance, impedance mismatch increases, causing a rapid reduction in total efficiency. So here from the graph we can see the sharp efficiency peak indicates narrow band operation, which is a characteristic of shorting plate PFA antennas. Effective area. So this is effective area. Now this effective area of the shorting plate PFA decreases with increasing frequency. So as the frequency keeps on increasing, the effective area, okay, it also keeps decreasing. There is the inverse relation. How? We know that lambda equals to C by F. So there is automatically an inverse correlation between effective area and frequency, and this is what we are seeing here. So this behavior is primarily governed by the lambda square dependence of effective area, and although antenna gain varies with frequency, the reduction in wavelength dominates the overall trend, and this observed variation confirms the inverse relation between effective area and operating frequency, and this is what I was saying. So this is clearly visible from the graph. Now comes radiation pattern. So the radiation pattern exhibits a broadside characteristic with maximum radiation normal to the path surface. So at the path surface, it is maximum. The ground plane and shorting plate suppresses back radiation, resulting in controlled directional radiation. And minor side lobes appear due to compact size of the antenna, but do not significantly affect performance. So the minor side lobes which we see, and the observed radiation behavior makes the shorting plate suitable for compact wireless application. So this can be a point to take note of. Next comes polarization ratio. So here we have taken a circular one. Circular one. So the polarization ratio remains close to unity, indicating stable and well-defined polarization characteristics. So see, it remains close to unity. So it remains close to 1. At every frequency you see 1.01, then slight increase 1.0125 and 1.0150. So this point comes in between there, and maximum it goes to minimum it goes to somewhere around 0.9975, right? So it is almost equal to our, just a second, it is almost equal to our unity. Near the resonant frequency, the polarization purity is high due to balanced weight components, and minimal variation in polarization ratio across the operating band ensures consistent radiation behavior, and this stable polarization response supports wireless communication for compact antenna applications. Finally, the conclusion of this PPT. The planar inverted F antennas PFA provides a compact and low profile solution for modern wireless devices. Shorting elements, shorting pin and shorting plate enable size reduction while maintaining good impedance matching. So this is why we are including shorting pin and shorting plate. Simulation result shows proper resonance with acceptable return loss, gain and radiation characteristics, and total efficiency and high radiation are achieved near the resonant frequency for all the configurations as we saw earlier. The shorting plate generally offers better current distribution. So the shorting plate, which we discussed just before this, offer better current distribution and efficiency, while the shorting pin provides structural simplicity. This is very clear, I think. Overall, PFA antennas are well suited for applications such as mobile phones, IoT devices, and communication systems, wireless communication systems. So that was it.